Do we start now? It is 7 o'clock.
It is started, sir.
Okay.
ISHRAE, Indian Society of Heating, Refrigerating and Air Conditioning Engineers. Founded in 1981 at New Delhi by a group of eminent HVAC and R professionals, ISHRAE now has a total of 41 chapters and sub-chapters.
ISHRAE gives you the latest industry insights of the HVAC and R and building industry and delivers latest technologies in forms of technical blogs, videos, and articles to people. It has more than 14,000 members and about more than 10,000 student members. ISHRAE releases various standards for HVAC and R building industry time to time. It organizes more than 800 events every year, including seminars, conferences, product presentation and more. ISHRAE also provides handbooks and guidelines. ISHRAE also has student chapters in more than 150 engineering colleges, to encourage students, and let them know about HVAC and R industry. Visit now, ishrae.in, for more details.
Good evening. Welcome all the participants to this webinar series on refrigeration applications by using natural refrigerants. This is a 7-session series being conducted on all Fridays from 7 p.m. to 8 p.m. I would like to thank our speaker, Shri Ramesh Paranjpey, for taking this webinar series. Just a second. Yeah, I would like to introduce our speaker today, Shri Ramesh Paranjpey. He's Mr. Ramesh Paranjpey. He's a fellow life member of ISHRAE. He has 50 years distinguished service, and he has also been awarded the 50-year service award from ISHRAE this year, 2020. Mr. Paranjpey is the member of the ISHRAE Fundamentals, which is a handbook, 2017. Member of the IAR USA, and by qualification, he has the post-graduation from IIT Mumbai in refrigeration, MTech in refrigeration. Professionally, he has around more than 40 years of experience. He has served at the various organizations like Voltas Air International Limited, Carrier Refrigeration, and mainly Vice President at the AC and R division from Kirloskar Pneumatics in Pune. He has also been the examiner, and he used to set papers for post-graduation in mechanical engineering for the Pune University. He has published more than 45 papers. He has conducted more than 300 trainings for various organizations in India and abroad. And the reason for getting ASHRAE fellowship, he's been meeting ASHRAE objectives in sharing knowledge and information through publishing papers and conducting training programs, as well as promoting arts and science of refrigeration and air conditioning. So he has a list of achievements. Our speaker today, he has been invited by German Chamber of Commerce to deliver the lecture on in Germany on ammonia pump circulation systems for low temperature applications. He has presented a paper at IR conference in Macedonia. Then he is the winner of the Breyer Systems Design Award in 2009. Is the winner of the Lifetime Engineering at ICE Danfoss Global Cold Chain Award in 2012. He has published books, a book on cold room solution for Emerson Technologies. He has published book for Danfoss Controls, how to use ammonia, making it easy and safe to be efficient during the term 2012 and 15. He has published a book on air-cooled design for cold storages for alpha level. Air cooler design, yeah. Okay, he has more than 700 projects he has executed in various in sectors in the industry, from ice cream making to process plants, fish, meat freezing, as well as air conditioning, such as international airports, office buildings, and shopping malls. Our speaker, Shri Paranjpey, is based in Pune, and you can note down his mobile number, the email, and also there is a website. Okay, now ASHRAE this year is 125 years old, and they have this year rightly awarded the Distinguished 50-Year Member Award to our speaker, Sri Ramesh Paranjpey. The Distinguished 50-Year Member Award is given to individuals who have been a member for a minimum 50 years and are a past society president or a fellow ASHRAE or a Distinguished Service Award recipient who have performed outstanding service to ASHRAE. Okay, so this is the recognition. There were 23 members, and Ramesh Paranjpey, fellow life member, ASHRAE Kothurud Pune, is one amongst them, and he is the speaker today. And this is one picture, which was, I think, it's written there, 2005, when he was getting the award from ASHRAE in 2005. So before I welcome, before Mr. Paranjpey takes in, I now welcome our ISHRAE President, Mr. Richie Mittal, to say a few words about this webinar series.
Thank you, Anish. And I would like to start with thanking Ramesh Paranjpey, sir. We are really honored that you have come on board with us to make a presentation, a series of 7 webinars, and all on natural refrigerants. So I am sure to see that we are already 300 plus delegates. So everybody is here to hear you out, sir. We are really proud of the awards that you have won. And at ISHRAE, we have thought of this year, we have thought that our refrigeration should be given more focus. Just to share with everybody, on a refrigeration day, our refrigeration chair is Anish Sinha and Mr. Manjunath is a vice chair. I must congratulate them because there were 27 such webinars which were conducted by chapters, sub-chapters all across India. So that, I think, it has never happened in the history of ISHRAE, or I would say anywhere, any society would have done that. So this year our focus is on refrigeration, because in ISHRAE R was normally missing, but this year we are very serious on R, and you can see this series. We also conducted a workshop which went full for refrigeration. So I am thankful to Anish and Manjunath ji to take up the refrigeration chair committee and take it forward. And thank you, Ramesh Paranjpey, sir, to present your experience, and we would definitely learn from you. Thank you, and over to you, Anish.
Yeah, thank you. So now I request Mr. Ravi to bring the screen from Mr. Paranjpey.
Okay, so I'm going to the main screen. I hope you are able to see my screen now, all of you.
Yes, sir,
we
it
can
is
able
very well seen.
Okay, and you can
अभी
hear
तुम्हारे
me
यहाँ से
very
आवाज
well.
आ रही
Okay, so I'm starting my presentation. First of all, let me thank ISHRAE President Mr. Richi Mittal and Amish Sinha, Manjunath, and all the people who have made this possible. My intention of conducting these 7 lectures is basically to concentrate on refrigeration. My experience, 55, 52 years experience in refrigeration field, and these 7 sessions, what we are going to conduct is basically on mostly on with ammonia refrigeration. But today's lecture, we are going to go, is an introductory lecture in which I am going to emphasize why one should use natural refrigerants. Of course, ammonia is one of the natural refrigerants, but I am going to prepare a background for further seminars, subsequent seminars with this today's lecture. With this, I think I will start my presentation. I will go to the second slide. Uh, the natural refrigerants. First, we must understand what are the natural refrigerants. The natural refrigerants are substances that serve as a refrigerants in the field erected refrigeration plants and air conditioning systems, as well as in domestic appliances like room air conditioners or your refrigerators, etc. These are alternatives to chlorofluorocarbons. These are basically alternatives to CFC, HFC, and HCFC refrigerants. That is chlorofluorocarbons, hydrofluorocarbons, and hydrochlorofluorocarbons. This is the Wikipedia definition. And unlike other refrigerants, they are not synthetic chemicals. This is very, very important. And all these natural refrigerants can be found in the atmosphere. The next I have defined here which are the natural refrigerants. So the natural refrigerants are uh, uh, starting with as per the ASHRAE designation starting with 7-digit. That is 7-digit are all natural refrigerants, and further 2 digits indicate the molecular weight of that refrigerant. For example, R717 is ammonia refrigerant in which there is 4, nitrogen is 1 and hydrogen is 3. So nitrogen molecular weight is 14 and hydrogen is each one is 1, so total 17. So 717, 17 is the molecular weight and 7 is the natural refrigerant number. Now what are the other natural refrigerants? It is the air 729, carbon dioxide 744, our water 718, and sulfur dioxide 764. These are all natural refrigerants. And next to that, hydrocarbons. Hydrocarbons do not start with designation at 7, but these are the hydrocarbons which are successful in refrigeration and in industrial refrigeration field and commercial applications. Which are these? That is ethane, propane, butane, isobutane, propylene, and the combinations of these refrigerants, that is isobutane, etc., etc. So these are also considered as a natural refrigerant because they are available in the nature. Now, why do we use natural refrigerants? Now we have to go to the little background, since we need now, as on date, no regret solution. Up till now, whatever refrigerants we have used, there has been some drawback, and people have come to the conclusion that these refrigerants are no good, and they are changing to always for the new refrigerant. For example, we started the field with CFCs, then we came to HCFCs, then now we are having HFCs, and now they are going to HFOs and other refrigerants. So every refrigerants have been found to have some problems. We'll look at it. So now we want refrigerants which are natural refrigerants and which has no regret solution, because all the properties of natural refrigerants are well known to people. Their effect on human beings is well known, and there are no surprises. So we need no regret solution. Then we need to basically very important issue is global warming. We need to overcome the global warming issue, which is today's the most important subject. We need better efficiency, and also we need easy availability as well as low cost for refrigerant as well as lubricating oil. These are the basically very important properties. Now, besides this, we go to some thermodynamic properties and go a little bit in more details. So, what are these? A high latent heat of vaporization. Now, we need to understand the meaning of it. See, it is the latent heat which makes refrigeration or air conditioning industry work. For example, in evaporator and condenser, when we call evaporator, the liquid refrigerant evaporates, and the refrigerant which is having higher latent heat will give better results. So any refrigerant should have as high latent heat as possible. Then it is a better refrigerant. Then it should have a high density of suction gas, because then your equipment will become compact. Your mass flow rate, your volume flow rate will be reduced. The refrigerant should be non-corrosive, non-toxic, and non-flammable. The next important point is critical temperature and triple point, and these should be out of range of a working range. That means critical temperature should be high and triple point should be low. For our normal operating range, in refrigeration air conditioning is right, let us say from minus 40 degrees centigrade to plus 40 degrees centigrade is an average range. Besides this, we go for very low temperature applications, but those are rare. 95% projects are covered in this range. And therefore, the critical temperature has to be higher than 40 degrees centigrade, and the triple point has to be much lower than minus 40 degrees centigrade. Then compatibility with other component materials, that is with condenser, with evaporator, with controls, with piping, the material should be compatible. Also, compressor requires lubricating oil, and the refrigerant should be compatible with lubricating oil. There are mineral oils, there are synthetic oils, and so many varieties of oil, POE oils, PAG oils, and every refrigerant has some compatibility with the lubricating oil. Then reasonable working pressures. We don't want too high working pressure, and we should not go below atmospheric pressure. For example, ammonia has the boiling point of minus 33 degrees centigrade. You can, up to that point, you can use at positive pressure. The discharge pressures also should be reasonable, 15 bar, 16 bar, 17 bar, not beyond that. Then the leak should be easily detectable, very important, and environmental friendly. This is the point which we discussed, and this is an important point. Now let us go, what is environment? The Earth's atmosphere, it consists of three layers, basically: mesosphere, which is 50 to 80 kilometers, then stratosphere, 10 to 40 kilometers, and troposphere, 0 to 15 kilometers. and in between there is an earth. So these three layers are surrounding our earth. Now, the most important layer is stratospheric ozone layer, which is between 10 to 40 kilometer size, and ozone is simultaneously produced from oxygen and destroyed into the stratosphere. Ozone layer filters harmful UV radiations, ultraviolet radiations. Let us see. In ultraviolet radiations, there are two types, ultraviolet radiation A and ultraviolet radiation B. A is not harmful, B is harmful, and this ozone layer protects ultraviolet B from reaching the Earth's surface. So this slide, environmental concerns affect the how refrigeration gets involved into it. Let us see. And there were two scientists, Dr. Roland and Professor Molina of California Institute of Technology, USA. And in 1974, they put forward a theory that chlorine content of CFCs were considered as God-sent man-made refrigerants, that is R12, R11, and so many other refrigerants, bromine, etc., etc., etc. And these people said that any chlorine content refrigerant, when it is released to atmosphere, that chlorine reacts with ozone and destroys the ozone layer. Now, as all of you know, in scientific magazines, lot of papers are published and lot of people read them and forget also. Very few people see the daylight in actual industrial practice. Now, this paper was a 1974 paper, and what they put forward the theory that ozone is an unstable oxygen molecule, that is O3, and instead of more stable molecule oxygen. So what happens? The chlorine reacts with O3, the oxygen is liberated, and ClO is formed. This ClO again reacts with O3, and stable molecule of oxygen is formed and chlorine is liberated. So the chlorine is a vicious circle, and this single chlorine atom is capable of destroying thousands or even millions of ozone molecules in the process. This was the theory which was put forward. This is a theoretical process which I have already talked to you, how it is ozone is destroyed. The last sentence is important. 100 grams of CFCs, chlorofluorocarbons, are able to destroy nearly 3.5 tons of ozone. Now, the next slide. What happened when the satellites were launched? 1974, this theory was put forward, but people forgot about it. But when the satellites were launched and the satellites took the photographs, they really found out that there is a big ozone hole. There is a big ozone hole in the center, and a lot of people, especially in the northern sphere and extreme southern sphere, Australia, Ireland, etc., people were getting skin cancers, eye cataracts, and so many diseases which were contributed to the ozone. So ozone was, because of the ozone hole, ozone was coming through and creating a problem. So everyone woke up and they said, this theory is very correct. And these scientists then got the Nobel Prize for this. Fortunately, I can tell you, at that time, I was involved in Montreal Protocol discussions on behalf of Government of India. Myself, Dr. Pachori of Tata Institute, Tata of Research Institute, and then at that time the Environmental Minister, Mrs. Menka Gandhi was the minister. All three of us went to California, went to discuss with US government to get funding for the Montreal Protocol for the Indian condition. So I was fortunate to meet both these Nobel laureates. Anyway, that is besides the point. Now you see the ozone portion. After banning of Montreal Protocol, CFCs were banned, and now we no longer use CFCs. R11, R12, no longer nobody uses. And you can see the picture now, the satellite picture, the ozone hole is practically now disappeared. The latest photo I will show you, this is the photograph taken on 22/4/20, just this April, and you will see there is no ozone hole. So we have solved one of the biggest problems, that is ozone depletion. Now, what are the remaining problems? The issues to be addressed now are global warming, energy efficiency, environmental friendliness solutions, and alternate technologies. The foremost, as you see, is global energy, the global warming and energy efficiency. Now, both these things are interrelated. How they are interrelated, we will see this. The ozone depletion is now solved, so we are looking at global warming. This is to be addressed. What happens? How the global warming takes place? The solar radiation, there are greenhouse gases surrounding the earth, and this radiation, solar radiation, penetrates and comes to the earth and is reflected back. The radiation is reflected back. If there are no greenhouse gases, this solar radiation reflected by the earth will simply be lost to atmosphere, and the average temperature of the earth would then drop down to minus 18 degrees centigrade instead of current average temperature of 15 degrees centigrade. So you can imagine certain global warming gases are a must to sustain the human life on earth. With GHGs in the atmosphere, a part of radiation is reflected and earth absorbs remaining radiation, warming the earth and making life sustainable. So, but beyond a particular point, if this global warming temperature starts increasing, then it creates a problem. Now, for example, these are the graphs which shows how the temperature increase is taking place and the global warming effect is taking place. So carbon dioxide percentage is going up and the global warming temperature is also going up. Now everyone will ask how carbon dioxide is responsible for global warming. So let's go to the next slides and we will see first what is the adverse effect of temperature rise. This is the Times of India article. Severe heat wave will affect 37% population, decline in marine life catch, loss of trees and plants, sea levels will rise. As you can see, everyone is aware the sea levels are rising. In Bombay itself, they have put lot of barricades at the Nariman Point and at the necklace to prevent sea from coming in. As all of us know, the Dwarka is already submerged. West Bengal, lot of sea water is encroaching on earth and there are a lot of floodings in Vishakhapatnam and that area. So sea level control is very, very important. And ice glaciers are melting at a very rapid stage because of the global warming. So these are all the adverse effects of global warming. And these are some of the photographs. We'll skip that. Now, everyone will ask why carbon dioxide? So if you see the global warming greenhouse gases, this is the slide which shows which are these gases, F gases, which contributes to global warming. And if you see carbon dioxide, 65% because of industrial processes, fossil fuels, and forestry and other land use. So total 65 plus 11, 76% is contributed by carbon dioxide. And therefore, control of carbon dioxide is very important if you want to control the global warming effect. The next slide shows how the atmospheric carbon dioxide percentage is constantly increasing. The allowable limit is around 350, but we have already exceeded that. We have gone to 408.55. And not only that, if you see the next slide, uh, this is the effect in between one slide. If you 0.1 kilowatt power consumption goes up, which contributes to global warming, so many bad effects will take place. 3 million cars, it is equivalent to taking off the road, 600 million planting of trees, and 9.9 billion of carbon dioxide plus nitrous oxide, etc., etc. So let us see what are the acceptable limits of CO carbon dioxide. As I mentioned, 350 to 450 is okay. 350 to about 1000 in a residential area or in a closed area is okay. But above 1000, complaints of drowsiness starts and ventilation suffers. 2000 to 5000, headache, sleepiness, increased heart rate, nausea, maybe bigger problems arise. Now I'll give you a simple example. When we are driving on the highway and our cars are, if they are AC cars, and if we are driving in a recirculation mode without fresh air, there is a icon on your dashboard which shows outside air circulation and one is only recirculation. If you drive in recirculation mode, the occupants are exhaling carbon dioxide and percentage of carbon dioxide goes up. The driver feels drowsiness, people feel drowsiness, and lot of accidents take place. So my suggestion, because I have worked a lot on car air conditioning designs in telco, always when you are driving on highways, always drive in fresh air mode. The power consumption does not go up because if you drive in fresh air mode. Anyway, this is besides the subject. I just wanted to stress the point, and therefore now we need to look very seriously at global warming. If we take CO2 as one unit, what are the contributions of refrigerants? R12, R11, R404A, R11 and R12 are no longer there, so let's not talk about it. They were a very high global warming also besides the chlorine content. But now we are using extensively, all of us, 95% of our plants use 404A, 410A, 407C, to some extent R22, and all our domestic appliances we use R134A. Now you can see 134A is 1300. Is 1 kg of CO2 vis-a-vis 1 kg of 134A. 134A contributes 1300 kg. 1300 kg is equivalent. So all these refrigerants contribute very high global warming, and therefore people have woken up now and they say let us ban also this 404A, 410A, 47C and 134A. R22 is also more or less is over. In another few years time nobody will be using it. But the last point, if you see ammonia, ammonia has zero global warming potential. The current situation, global, very important slide, air conditioning and refrigeration industry. Whatever is the global energy production, 40% of the global energy is consumed by air conditioning and refrigeration industry, by our domestic refrigerators, room air conditioners, central plants, food preservation, etc., etc., etc. And the next point is important. 40% of building power, if you do an air conditioning of a plant, is consumed by air conditioning industry. If your building requires 100 kilowatt, 40 kilowatt out of that is required only for air conditioning. This is not my comment. This is ISHRAE Journal, September 2004, 2014 article. Now let's go to the next slide. A lot of people feel, 99% people feel, oh, that means refrigerants are contributing to global warming. And when they leak out, they contribute to the global warming. This is a myth. The global warming contribution because of the leakage of refrigerant is only 10%. The indirect global warming, which is known as TEVI effect, total equivalent warming impact, is 90% because of the energy consumption of a refrigeration plant. So it is important to note that 90% global warming is from energy consumption, and hence we need to concentrate more on energy consumption consumed by the refrigerants besides leakage of refrigerants, which contributes 10% global warming. The reasons for considering these alternatives now. Montreal Protocol was in September 87. The subsequent agreements which have taken place, but Montreal Protocol, that time the greatest issue was CFC, that is chlorine content. And although 187 countries participated, nobody did consider about global warming or did not talk about it also. Then subsequent Kyoto Protocol took place in 1997, and they then said, oh, now the global warming is a major issue and we should look for what to do about these refrigerants. The EPA SNAP rule, USA 2016, decided to phase out 134A, 404A, etc. This has to still meet the, although industry has issued it, the government approval is yet to be received for this. Finally, it resulted into a Kigali agreement in October 16 to phase out HFC, high global warming refrigerants. And you see, this 186 countries on 16 countries, Montreal Protocol, subsequently Kyoto Protocol, Kigali Agreement, very important last agreement, was reached in 2016, just 3 years back, 4 years back, and they decided that these HFCs to be banned. These HFCs should be phased out, gradually to be phased out. And it is also, there is a provision, if a particular country who is a signatory for this does not follow this practice, then there are penalties for non-compliance. So very, very seriously people have taken the global warming effect. Now this is today's slide in ISHRAE. If you see, those who are ISHRAE members must have read. I just added this slide at the last moment. Sustainable cooling is a key to achieving the goals. Phase out HFCs under Kigali Agreement potential to avoid up to 0.1 degree centigrade warming of global warming up to 2050 and 0.4 degrees centigrade by 2100. Energy improvements simultaneously, besides phasing down, can potentially double the climate benefits. A very, very important statement today in ISHRAE News. They have made this, and there is a conference going on in UK to discuss these issues today. Now, USA SNAP rule, significant new alternative policy program, decides to phase out 404A, 410A, 517 as a long-term solution. This is a Europe document, and this is a statement made by them. So, which are the refrigerants now will be unacceptable? R12 has already gone, 502, 507, 404A, 407A, R22, 407C, and 134A. All these refrigerants will be phased out. What will be left is 404, 448A, R32, and lastly, if you see last four refrigerants, hydrocarbons, that is propane, isobutane, polypropylene, carbon dioxide, and ammonia. Now, these last four, as we discussed, are natural refrigerants, and ISHRAE journal therefore issued a statement in 2017 that changing rules around the use of high global warming potential refrigerants have been one of the hottest topics of HVR industry, and following ozone depletion and SNAP rule, we need to phase these out, 404A, 507. So the next slide will show the phase down schedule, what has been agreed upon from 2015 as 101%, and then gradually slowing down. For example, 2019, 10%, 2024, 40%, 2029, 70%, and by 2036, 85%. That is all the new equipment except the replacement equipment. Now let us look at the refrigeration timeline. Very important time slide. You will see sulfur dioxide was used in very early stages as a domestic refrigerant. Then it was not. It was phased out. The CH3Cl, CFCs, they came, they vanished. HCFCs are now also, HFCs are also in the dotted lines, they are going to be phased out. Hydrocarbons were being used, but in between they came, they broke out. In between they came, they broke out. Carbon dioxide also was used some time back, but it came again, there are broken lines. Only unbroken line, if you see, is the ammonia refrigerant. Ammonia refrigerant, since the refrigeration air conditioning industry started, we have been using ammonia refrigerant throughout, from beginning till date. And it is a very good refrigerant. We'll talk about it subsequently. But in cold storages, ice plants, industrial process plants, ammonia was being used. In between, these CFCs came and they were used for comfort air conditioning, domestic air conditioning, and other places. But CFCs, HCFCs are now going out. So again, the wheel is turning and we are coming back to natural refrigerants. If you see this slide, it sums up atmospheric life, ozone depletion, and global warming potential. I will not read this entire slide, but atmospheric life is also very important, because these refrigerants, 404A, 410A, 507, it has some atmospheric life, 15 years, 16 years, and because of the Earth's rotation, they go into the stratosphere, and then global warming and other ill effects take place. Whereas all these hydrocarbons and ammonia, if you see, atmospheric life is nearly zero. That is, as soon as it leaks out, it is dissociated into its basic components, and therefore there is no atmospheric life, zero ozone depletion potential, and zero ozone depletion potential for ammonia. This is very important to note about ammonia properties. Now let's come to ammonia. Ammonia is a natural refrigerant and scores above all other refrigerants. It is natural production. 90% of it is used as a fertilizer, and a purified grade is used in refrigeration air conditioning plants. What are the other advantages of ammonia? We are going to deal this in our next session too, but these are the quickly summing up: zero ODP, zero, etc. Base thermodynamical properties, very important. Now, why this is important? Because of the global warming. It will consume least possible energy And therefore, even in air conditioning plants, people are started using now ammonia as a refrigerant. It is a very low cost. The man-made refrigerants cost 3,000 rupees a kg, 4,000 rupees a kg. Ammonia costs only 60 to 70 rupees a kg. Lubricating oil is a mineral oil, very, very inexpensive. We don't have to use PAG oils or POE oils. All the equipment is manufactured in India, compressors, condensers, evaporators, etc. The equipment parts are available all over the country. The refrigerant is available all over the country, right from Kashmir to Kanyakumari. The refrigerant is lighter than air and does not accumulate in the machine room if it leaks. Since ammonia smells, leaks are easily detectable. A 5 ppm leak is detectable, whereas all other refrigerants currently what we are using, they don't have smell. So only when our cooling effect is lost, then we realize our refrigerant has leaked out. And by the time the cost is prohibitive to replace this. It does not mix with oil, very, very important property, and can be drained because oil has no cooling effect. If the oil circulates in the system along with the refrigerant, it takes certain portion of cooling effect of the equipment. So oil should not be present anywhere else in the system except for the lubrication of the compressor. These are the this is the slide which I have prepared, which is an energy consumption, very, very important slide. I have considered all the applications. For example, our chilled water plant applications, our condensing temperatures, I have taken 40 degrees centigrade because all ISHRAE books, they take 35 or 30 degrees centigrade. So I have taken 40 degrees, which is common in India. And chilled water plants, we use 12 degrees, 7 degrees, so 2 degrees evaporating temperature. Secondary fluids for process plants like brine, if you use ethylene glycol, propylene glycol, minus 5 degrees centigrade. For food preservation, that is ice cream, meat, fish, minus 20 degrees centigrade. So I have taken minus 25 as evaporating temperature. And lastly, the freezing application, which is minus 40 degrees. All freezing applications are done at minus 40 degrees centigrade. And if you find the COP, coefficient of performance, is the highest in all these four applications, if you compare 410A, 134A, 404A, and R22, currently used all refrigerants. Ammonia has the highest COP in all these ranges. And therefore, in all these ranges, my strong recommendation is we should use, as far as possible, try to use ammonia. I'm not saying ammonia does not have adverse effects, but we must concentrate on overcoming these drawbacks rather than go on developing new and new refrigerants every time. We as engineers and scientists, we love to calculate, to do formulas and develop something new. And then we feel very proud that we have done some new research. But remember, there is a solution available for every problem in nature. And ammonia is a natural refrigerant available. Try to work out with ammonia as much as possible. Our next sessions, we will concentrate more on that. But these are the fields of application. I will not take more time in running through these. These are ice plants, cold storage, of course, all process plant applications. But the next slide, you will see very, very important slide. Even all air conditioning plants globally, people are using now ammonia because in the big air conditioning plants, ultimately we circulate chilled water and plant room is away. So whether the chilled water is produced with ammonia or whether with other refrigerants, it does not matter. So let us use most efficient refrigerant And therefore, all these airports, Oslo, Heathrow, Singapore Airport, Zurich Airport, and not only that, the telephone exchanges in Copenhagen, the train stations, which has a lot of occupancy, Roche headquarters, that is administrative building, all these buildings are using now Johnson Controls building for 500 kilowatt air conditioning. So everywhere globally, people are using, even for air conditioning, now where chilled water is used, ammonia as a refrigerant. So having talked about ammonia, we are going to discuss about ammonia in our subsequent sessions. But let's talk about other refrigerants, global warming. These are natural refrigerants, and carbon dioxide as a refrigerant, which is getting renewed interest. The carbon dioxide is most promising refrigerants, especially in the cold climate countries in Europe. Its critical temperature is very low, is 31 degrees centigrade. So in India, you cannot condense carbon dioxide in a single stage operation because our condensing temperatures will be always higher than 31 degrees centigrade. Operating pressures are much higher. The operating pressures of carbon dioxide are 60 to 70 kg per centimeter square. So all our equipment, which currently we use 15, 16 kg, has to be developed and designed to use this refrigerant. High, but it has advantages: high volumetric efficiency, non-flammable, non-toxic, compatible with normal oils, and excellent performance for the heat pump duty. These are all the advantages of carbon dioxide. Low GWP, no ozone depleting potential. GWP, as you see, is only one. It is a natural refrigerant, non-toxic, non-flammable, high density. The plant becomes extremely small. Your pipeline sizes become 8 millimeters, 10 millimeters, 12 millimeters size. So a full air conditioner can be made as a cassette air conditioner and can be fixed into your glove compartment of a car. You don't have to put anything under the bonnet. So it is very compact refrigeration air conditioning plant. Very small piping, high heat transfer coefficients, very small condensers evaporators, very low pressure losses, high efficiency in subcritical cascade systems, positive pressures in low temperature applications, and low cost. Hardly there is any cost for carbon dioxide. But what are the drawbacks? Very high discharge pressures, as I mentioned, very low critical temperature, 31.8, limited flexibility in applications, and cascade coolers. Atmospheric condition, 400 ppm in atmosphere is allowed. Odorless, the smell is not, it is not detectable. So carbon dioxide as a refrigerant, what are the applications where we can use in India? We can use for high stage R134A, 404A, which we are already using. And for low stage, we can use carbon dioxide. Or alternately, I would suggest high stage ammonia and low stage carbon dioxide. This is a very, very popular application all over Europe and USA, especially for the supermarkets. The ammonia plant is in the remotely located, and all your supermarket equipment with carbon dioxide is circulated as a secondary refrigerant. Or you can use secondary coolant as a base in supermarkets, as I mentioned. So a carbon dioxide is again forming renewed interest in use of, for example, our Olympics, they banned use of 134A, Australia. So a Coca-Cola company used in 134A and 550 liter refrigerators carbon dioxide. And they found that it consumes 20 to 30% less energy compared to 134A refrigerant. So you can imagine our concentration today, the entire program is global warming, and we are trying to reduce global warming. And 90% global warming is because of the refrigerant power consumption, and 10% is because of the leakage. Keep this, which is I am again and again I am repeating. This is a carbon dioxide ammonia cascade package, which is a factory made package and a very compact package. Both are using reciprocating compressors. This is an ammonia CO2 used as a brine storage. CO2 is used circulated into the cold rooms, and this is a machine room for fruit storage in Holland. So this is a carbon dioxide application. And you can see this Germany, the Roxetta company uses carbon dioxide, and they have sold more than 2,900. That is very old slide. By now it must have cost 5,000 units. So this is very, very important. This is a package built with carbon dioxide as a package. The next slide, if you see, carbon dioxide has been used for bus air conditioning. And in 1996, it has already clocked 1700 hours. How much hours it must be clocking now, you can imagine. This is, of course, used in a very cold climate countries for bus air conditioning. The next refrigerants we come to hydrocarbons as refrigerants. Since our time is approaching very fast, I may exceed for five minutes more, but hydrocarbons as a refrigerant are used in domestic refrigerators and freezers. For example, Godrej, in all their refrigerators use isobutane. My domestic refrigerator at my home is Godrej refrigerator and is performing very well. Bottle coolers, ice cream freezers, commercial refrigerators, beer coolers, dehumidifiers, etc., etc., as also small air conditioners. All of them can use hydrocarbon refrigerants. These are the most popular hydrocarbon refrigerants: butane, isobutane, propane, propylene, ethane, and ethylene. These are their boiling points and other characteristics. Let us go to the next slide. These are the substitutes. This slide is important. 134A can be substituted with isobutane for household refrigerators. 134A can be substituted with propane isobutane mixture for commercial applications. 404A can be substituted with 290 R1270 and their mixtures in industrial petrochemical plants. 407C can be replaced with propane and propylene mixtures for air conditioning and heat pumps. 410A can be used for mixtures of propylene ethylene mixtures for this thing, and R23, R14 for low temperature cascades. R227 can be replaced by isobutane for high temperature application. So for every application you will see there is a hydrocarbon available. Hydrocarbon as a refrigerant has been used in more than 300 million domestic refrigerators. Propane in central air conditioning system consumes 10 to 30% lower energy, and Unilever uses propane in their 360 liters ice cream freezers compared to 404A, and they have 9% lower power consumption. Hydrocarbon Pepsi has compared the results with isobutane, and they say 27% less energy compared to R134A they are using when they use isobutane. So Pepsi, Ben and Jerry, Unilever has been very widely used. They are using these refrigerants. Energy efficient propane HC290 is being used by room air conditioners, small room air conditioners by Godrej and Boyce. This is a 290 propane air conditioner in China. More than 3 million air conditioners have been sold by GREE. Key factors in propane air conditioning. We will not go into more details of this for the want of time, but these can be used in production lines in China. There are so many production lines and energy efficiency, etc., etc. One can use these. Propane for air conditioning, the municipal corporation has installed this. This is a Euromon slide, requires very less quantity and system is working since 2011. Propane for heating and air conditioning can be combined, it can be used. And this is a propane CO2 cascade. This is a propane refrigeration package. As you know, many companies in India are also producing propane packages along with the screw compressors. And this is used in Rajasthan, one of the power plants. This is a propane package used in petrochemical plants. This is a propane water and brine chillers. And this is the history of refrigerants. These are my few concluding slides. Our first generation, whatever was working, we used in 1830s and 1930s. That is ammonia, sulfur dioxide, carbon dioxide, various hydrocarbons, methyl chloride. Then the second generation, safety and stability became important, and ammonia continued to be used. CFCs were introduced, R11, R12, R22, 50. Now the third generation, ozone depleting, the CFCs are banned, no more CFCs. We are using 134A, 410A, 404A, ammonia, and many hydrocarbon blends. And now the fourth generation, fewer societies, we will be continuing use of ammonia. This 120, 1, 2, 3, 4 YF, ZD, HFOs, these have been introduced, but natural refrigerants, CO2s, hydrocarbons, and ammonia are finding new interest. Our subsequent seminars, which are going to be held, I'll be talking a lot about these other aspects. And therefore, my last slide, which I want to show, we started in 1834, and now the cycle is completing. We are coming back again with CO2, ammonia, hydrocarbons as a natural refrigerants for our all air conditioning and refrigeration applications. Again, I will repeat, for two reasons: for global warming and energy efficiency. These are the two major issues our current generation as well as next generation will be facing, and they will have by the time full solution for these problems. And with this alternate solution, phase out, my suggestions, phase out all man-made synthetic chemicals, concentrate research on use of natural refrigerants, research on alternate technologies like solar power, wind power, thermoelectric, magnetic materials, phase change materials, use nanoparticles to improve heat transfer coefficients in heat transfer. And finally, the last sentence I read, have no regret solution as a long-term measure. Nature has solution for every problem and is the ultimate in technology. You will find solution for everything in nature. With this, I close my presentation. I have exceeded about 5 minutes, and all your questions you can give to ISHRAE or you can send me a mail. My web page is there, where all my articles are there. My cell phone number is there, and my Gmail address is there. You can write to me any questions you have, and I will give you information and replies free of charge. You can ask me any question related to refrigeration, not necessarily for the today's presentation, but I have decided now that rest of my life I will not charge anyone any charges. and all my consultations will be free of charge. So with this, I once again thank you, ISHRAE headquarters, Mr. Richi Mittal and all his team and the BOG for giving me this opportunity to present my first presentation. My next presentation will be next Friday, where I'll be talking more on ammonia refrigeration. Thank you very much. And with this, I stop my presentation. Thank you.
Thank you, sir, for this wonderful presentation. There are few questions which have been asked, and we will be passing on
Yes.
these questions to
Yeah.
Mr. Paranjpey. I would like
Huh.
to read a few questions now, and the answers can be shared by, will be dealt by Mr. Paranjpey.
Yeah, I know. I'm aware that a lot of engineers in India also are building up plants, air conditioning plants and other plants, and using these synthetic, using natural refrigerants in their plants.
Okay, okay. So
The
there is
efforts are
one.
already being done, but 90% people are still reluctant. Very few engineers like Sina Saab and others, they have used already in their plants, process plants, uh, uh, process hall air conditioning plants, and other industrial plants for air conditioning ammonia as a refrigerant. Thank you very much.
Thank you, sir. So this one question by Mr. Ramalingam C says, respected sir, for a small cold storage application of 500 to 600 cubic meter operating at minus 20 degrees centigrade in India, whether going for a refrigerant system with other than ammonia is better in terms of efficiency, automation, and future sustainability.
Yeah. So ammonia will be the most efficient refrigerant for this application.
This is only five.
There are
Sir,
slides
this
in
says,
our next seminar. You kindly attend it. I'll explain it in detail. We are going to have one more seminar also on cold storage design, in which I will discuss in more details. That is on 31st July, session number 5. Steps to build modern and energy efficient cold storage. At that time, I'll discuss all these issues related to cold storages. Okay. Thank you.
okay, sir. Okay. Then there was another small question here by Pushkar Sharma. He says, sir, you mentioned 40% of global warming is affected by refrigeration and air conditioning, out of which 90% is from energy consumption. Can you please teach, if we use ammonia and R134A for a 10 TR refrigeration system, both will use almost same power consumption, then why still R134A is responsible more than ammonia? Does it because manufacturing of 134A uses more energy than manufacturing ammonia? Sir, you can take this question now, or
That also
you can
I will show you in my next, what we call TEVI effect, that is total equivalent warming impact. Now, total warming impact takes into account the production cost of refrigeration equipment, production cost of refrigerant, installation cost of refrigeration equipment, life cycle cost of refrigeration equipment. Not only that, when the plant is to be destroyed after its life is over, what is the cost involved in destruction of this? So a combination of all these parameters are taken into account in life cycle costing and in total warming impact effects. And I will, in my next session, I am going to discuss this in greater details, that how ammonia scores all over these other refrigerants, including 134A, which you just now mentioned. Okay.
Okay, sir. Okay, then of course, this question is toxicity and size of plants or the problems with ammonia as the refrigerant. What all has been done on that? I think you will be discussing in the future courses about this. Then the next question was, how is the efficiency of ammonia refrigeration system versus ammonia CO2 as a secondary for food industry application with +2, +4, -40 and -20 degree centigrade?
Yeah.
So,
yeah.
So these questions, I'm sure you'll be, please go ahead, sir.
I will cover this also next, but just to briefly answer your question, see, CO2 is at positive pressures below -30 degrees centigrade. So at -40 degrees centigrade, ammonia works under vacuum, and there is a chance of air leaking through shaft seal inside the plant, etc. So a cascade, ammonia for the high stage and carbon dioxide for the low stage, could be an ideal combination. I'm designing just now and installing one plant for plate freezers working at -40 degrees centigrade using ammonia for the high stage and low stage carbon dioxide as a refrigerant. And that combination works very well for ultra low temperature applications. But up to -30 degrees, because carbon dioxide, as I mentioned, is a high pressure refrigerant and the equipment is expensive. So ammonia equipment up to -30 degrees centigrade and the power consumption figures will be very competitive with ammonia refrigerant as against the combination. The combination is used because in many places ammonia is not allowed. Like supermarkets, you will not be allowed to use carbon dioxide ammonia inside the premises. So therefore, the cascade will be very useful. Ammonia in the plant room and CO2 into the process halls or into the supermarket. So these are the combinations. Okay.
Okay, sir. One last question. Of course, there are many.
I think.
Yeah, this is a very simple question. That's why I just wanted you. When we are saying ammonia refrigeration system, ammonia refrigerant is pure ammonia or mixture of water?
Ammonia mixture of water. Okay, water and ammonia are fully miscible, and therefore you will not, even if there is 5% water into ammonia system, you will not be able to detect it. Only your pressures and temperatures will not be as per the saturation properties. Therefore, in ammonia plants, it has been found that people say there is no water in our system, and buckets of water has been removed from ammonia system. This is not in India, this is in Europe. There is a paper published by Johnson Control which says that nearly 200 liters, 300 liters of water was removed from the systems in cold storages without the customer being aware of it. Ammonia and water are fully miscible, and therefore I would suggest, if you want to design an efficient refrigerant plant, you must have a water rectifier installed into an ammonia plant, and that will take care of removing water from your system. Otherwise, even if this water is there in the system, your system will continue to work. Nothing will happen to the system. Okay.
Okay, sir. Thank you. So generally in ammonia refrigeration, it is anhydrous ammonia and the percentage will be 99.9 and more. So water content is 99.95% of ammonia. Water is not to be part of ammonia. Okay. So I would like to invite Mr. Manjunath, the Vice Chair, Refrigeration Committee, ISHRAE HQ, to do the to give the concluding remarks.
So thank you very much, Anish, and it was such a wonderful talk. Actually, many of us know a little bit about several things. but Paranjpey sir knows everything about everything in the refrigeration field. And it was a very, very scholarly presentation, sir. We thank you from the bottom of our heart. It's really a wonderful talk that you gave us. I would also like to take this opportunity to say that a very philosophical statement that you made, that there is a solution for every problem in nature. And I think you set the context very well for the entire lecture series that you're going to do. I'm sure all the participants are waiting for your next lecture, and it will be much more interesting than what all you gave us today. As we go forward, there will be more cases, there will be more case studies, there will be more technical discussion and presentations. We are all looking forward to that. And thank you so much for being so kind to give us all this on a platter to so many of the people. We have a wonderful attendance today, and I thank each and every delegate or participant who has logged on and taken advantage of this great educative session. I would like to thank Richie Mittal. Yeah, I would like to thank. I would like to hand over to Anish so that he can do the vote of thanks.
I will send the presentation in a PDF format to ISHRAE, and I think you can circulate. Whosoever wants it, you can give it to. I'm not going to hide anything. I'm going to share all my presentations with ISHRAE, so it can be published also.
Thank you so much.
That's wonderful, sir. That's wonderful, wonderful. Sir, again, thank you for today's presentation. And I would like to thank our ISHRAE President, Richie Mittal, for his always thrust on the refrigeration in ISHRAE, and he has been supporting us with all the programs which under the refrigeration group. I would like to thank Mr. Manan Vora, the national chair for programs, Mr. Sandeep Galotra, the national chair marketing, and all the chapter chairs, all the chapter presidents of the 43 chapters of ISHRAE, chapters and sub-chapters together, and the refrigeration chairs of all these chapters. But for your efforts, it would have been very difficult for us to conduct this seminar. I would like to thank the HQ team of Jitendra Harsh and Ravi Thakur for their support. Thanks a lot.
I'm
Okay,
sure
bye.
those who heard today's presentations will certainly be present next Friday. But my suggestion is, please try to involve more and more people. Let's do a little bit of marketing, and because such opportunity may not come again for the people to hear and to get this presentation. So more ISHRAE members, please let's do that. And let's meet again next Friday. Wish you all the best and see you on next Friday. Thanks a lot.
Thank you very much, sir. Thanks a lot.
Bye.
Do appreciate it, sir. Thank you. Bye.
Bye bye. So our yeah, we can close this.
Thank you, Ravi, Jitender, and amazing show. Thank you.
Thank you, sir. Welcome.
We just finished.